counting. It is simply counting the same thing as the second time. Therefore, you can't keep. Therefore, this also goes away as a Pauli disallowed state. And what you should really write is, you must say that this is the same as 2. This is the same as 2. Others will be fine. And when you add the others, what will you get? This will be a -1, and that will be a 0, and -1, and that will be +1. This will be 0, and that will be 0, 0, and that will be 1. As I said, just get the feel for how you do it. I will send this to you, and then you can take a look at it. Let's write, I'll write a couple more. Okay, just 2 more. I won't write all 36. Pretty early. We will just write more a few. 2. There will be 6 sets of these, right? There is 6, there is the other 6, 36. That's how we will get. We will do maybe 24. We will write 24 so that we clearly understand which to throw out and which to keep. And the last 2 I will just, and by that time you will see the pattern in this. And then you will know what's going to happen. Let's write the next one. Okay. What do you think I should proceed to the next one now? I have done minus, plus, minus 1 plus. So what should be the next one? Start with 0 and a minus, and then write all the other 6 states. That's how we go about doing this. 0, minus 0, minus 0, minus 0, minus 0, minus plus 12, 13, 14, 15, 16, 17, and 18. And you will see why I'm putting these numbers, because it helps me later. I just say that this is the same as 2, and you know what I'm talking about. And what will happen here? It will be minus 1 plus 0 minus 0 plus 1 minus 1 plus. I exhaust all my 6 possibilities on this configuration. What is this going to be? A minus 1, minus 1. What is this going to be? A minus 1, 0. What is this going to be? A 0 and a minus 1. 0, 0, 1, minus 1, and 1 and 0. We have written all the comments, but tell me which ones will survive and which one will not survive. What about the first one? First one is same as, yes, it is minus 1, minus 0 and a minus. Minus 1, minus 0 and a minus. So 0 and minus was actually the first electron, and minus 1 and minus is for the second electron over there, whereas here it is for the first one. So they have simply swapped labels. Therefore, again, it is not to be counted twice. We count it once, you don't count it twice. This guy goes off. You can see the pattern. The first entry here was same as 2. The first entry here is same as 3. The next one is going to give me same as 4, and then will give me same as 5, and then so on. What about this one? Is it same as something else? Minus 1 plus 0 minus. Minus 1 plus 0 minus. So it's the same as 9. It's the same as 3. This is out. What about this guy? It's your classical understanding of the Pauli principle. This and this are same, this and this are same, everything is same. Therefore, this is out because all the electrons, both electrons seem to have all their quantum numbers the same. Therefore, they are out. So you can see the pattern that's coming out of this. The pattern is, in this, the first entry will be one of those entries in the first group. The second entry will be one of the entries in the second group. And the third one is simply a bunch of quantum numbers being the same on both electrons. Therefore, that's out. I didn't lose anything out here. I lost 1 out here. How many did I lose here? 2. How many did I lose here? 3. What's going to happen here? I'm going to lose 4. I'll get 2 left. The third one, what will I get? 5. Last number meant nothing because all these already have been taken and therefore I don't have to worry about it. And this will happen if you write it in this particular order. If you write it in a flip-flop manner, then you will not see what's happening. That's the reason why you will do it this way. So you don't have to really write all 36. By the time you get to 24, you know what's happening. And in the fifth group, there's only one. You just write that one because you know everything else is going to get away. And that's how you get all your counts. So we got this. Then what's going to be the next one here? 0 plus 0 plus 0 plus 0 plus. What happened? What about the first one? You know where to look for. 2 got thrown away, 3 got thrown away. So you just look for the 4th guy up there, and that's what that will be. So this is exactly the same as 4. That's how. 9 got thrown away here. So when you look at this fellow, where do you look at this? You look at 10 and see what happens. It's 10. So this guy gets thrown away because of that. Now this fellow will be some constituent over here. And which one is that? It's 16. And therefore this fellow is 16. That's how. And what about this fellow? It's 0 plus 0 plus. Therefore that's out. So what's going to remain? 2 will remain. And what are those 2 going to be? That's 0, sorry, that's 1 and a 0 and 1 and 1. That's it. So I got 5 out here. I got 4 out here. I got 3 out here. I got 2 out here. How much is that? 9, 12, and 2, 14. And the next one, I said I won't do it. But which one do you think will survive? The last entry has to survive. And what's the last entry going to be? It's going to be minus 1. Sorry, no, plus 1. Minus 1 and a plus. And what is that going to be? A 2 and a 0. You will lose 5 out there, and therefore you will be left with 1. And in the last one, what will you have? Nothing. So you don't have to write it. You know all 6 will be lost. So don't waste your time writing out all the 6 and then figuring out that it really doesn't mean a thing at all, because they all would get knocked off. 5 of them would get knocked off because they were actually counted earlier, and 1 of them would get knocked off because all these 4 quantum numbers would have been the same. So we don't have to write this. So we basically have counted all 36 states. We have looked at all 36 states notionally. We didn't look at the last 6, but we knew we didn't have to look at it. We have looked at all 36 states notionally, and we have been able to figure out which of these combinations are really Pauli allowed. It gets that difficult when you get to P2. When it was S2, there's no big deal. You could figure it out by just looking at it. There's only one combination, and you knew that combination would not work because it was simply a question of no 2 electrons having all the 4 quantum numbers the same. Over here, it is not just that. It is not just a question of no 2 electrons having all the 4 quantum numbers the same. You also have to worry about configurations which are counted earlier. And that's why we have to do all this. And when you do all this, so now totally how many do you get configurations? 15, right? We came up to here and we said 14, we get 1 more, and that makes it 15. And if you go back and count the number of states you have, triplet P, singlet D, singlet S, it will be 15. So it looks like we are doing okay. We got the same number of states, which all adds up to the degeneracies of the 3 states we wrote out earlier. Now the question is, with this information, how do I know that this is triplet P, singlet S, and singlet D? It's not, that is not clearly obvious. So we have to find out a way by which we can do this. Okay? So what I'm going to do now is the following. I'm going to summarize this big mess out here into something that's more tractable. And then we will see how I can make sense out of this garbage. What I'm going to do is the following. I'm going to make a little matrix of numbers. This is capital Ml. This is capital Ml. What are the possible values of capital Ml that I have got from here? Capital Ml can be -2. It can be a -1. It can be a 0. It can be 1. It can be +2. So all these possible states. So I will write here -2, -1, 0, 1, and 2. What are the possible MS values I have got? M capital S. -1, 0, and 1. Now let's see what we can do with this, whether we can summarize this into something like this. Well, what is this configuration really? This configuration is, let's take this one, this is allowed. Capital Ml is -2 and capital M capital S is 0. So what I will do is, I will go here, Ml is -2, Ms is 0. I'll just put a dot here, meaning I have one state that actually corresponds to this particular combination of M sub L, M sub S. So this actually goes here. What is this fellow? It's -1, -1. So where would that go? That goes here. Then I have -1, 0. Goes here. Then I have 0, -1. And then I have 0, 0. So I'm just sort of putting all this into something that's more, easily recognizable. Here I have what? -1, 0. -1, 0. And then it is -1 plus 1. Then 0, 0. And 0, 1. Okay. That's what you have to do. I'll just simply write this now because you know how to get that information and put it out here. And what you will have is the following. You will have this. So all that table will actually fit into a dot diagram or something like this. So you will have all these things. And this is basically what the components of adding all these vectors is going to give me. As I said, we have to see how this means or what this means in terms of the term states. So we wrote all this out, which was not very difficult. It's just trivial, just tedious, but we know how to do it. But once you have done that, we summarize the whole information into a dot diagram like this. This is what it really means. And now we've got to see how we can unearth information out of this diagram to get the states that we want. This is the final link. Let this be here. We will come to that a little later. But let me work backwards. Let me work backwards. Suppose I have a table like this. Let me give you a singlet estate. I will give you a singlet estate. What's the capital L value for S? L is 0. So what is ML for this fellow? Right? What is S for this guy? 0. And what is MS for this guy? So if I give you this state, where would this state fit into this diagram? It must have ML equal to 0 and MS equal. That's the only possibility, right? There's nothing else in it. So ML must be 0, ML must be 0. So where do you think this fellow would fit in here? That's it. So if I ever gave you a diagram like this with just one dot in the middle, what state am I referring to? Oh, it must be a singlet state I'm referring to. See, I'm now getting this information backwards. If I gave you this diagram and I told you what is this diagram going to be corresponding to, then you know that this diagram must correspond to singlet state. Keep this in mind and let me erase this. Supposing I gave you a singlet D state. What is L for this? 2. And what is ML for this? Minus 2, minus 1, 1 and 2. And what is MS for this? So if I have to put this guy in a dot diagram, what are the possibilities I am going to get? MS can be 0 and ML can be minus 2. So where would that fit? Here. MS can be 0 and ML can be minus 1. So where do I do? I put a dot here. 0 and a 0. 0 and a 1. 0 and a 2. There are 5 possible only components for this. And therefore, if I ever give you a dot diagram like this with 5 dots in here corresponding to 0 over here, that straight away tells me I am looking at a singlet state because MS is 0. And what are the ML states spread over? The ML states are spread over minus 2, minus 1, 0, 1 and 2. So immediately it tells me I am really looking at a D state. So if I give you a dot diagram like this and I told you what is the state going to correspond to, what state would that be? It has to be a singlet D state. If I give you a dot diagram which is this, what is that going to be? Yes, it's going to be a singlet P plus a singlet S. If I give you a triplet P, what would that look like? L equals 1 and therefore ML must be equal to minus 1, 0 and 1.